Hey everybody, it's Stickman Science here with my first video in the series, learning OChem in 90 days. Before we begin, I want to say a huge thank you to everyone watching, and I want you to know that you can succeed in OChem. You may have to spend a little bit more time on the subject than you're used to, you might struggle a lot more than you did with other classes, and you might need to practice a whole lot more. I know the struggles that come with this course, and as a pre-med student myself, I know that it seems like the grade in a single class can change your entire future. And I want people to be able to fulfill their dreams of having any job they want. I don't want a single class to define anyone's success, so just give this video a chance, like and subscribe if you enjoy this content, and click the links down below in the description for some practice and extra help. I want you all to do well, and hopefully I can continue to make better quality content since right now I'm literally recording this on an old pair of Apple earbuds. Anyways, I'd love to help you all out. Thank you, and let's get the video started. To start us off, I'm going to begin with a very short review of general chemistry concepts needed to really study organic chemistry. I'm not going to be able to cover all the concepts in this video, but I'm going to hit the highlights that I think are the most important and foundational things. Alright, first of all, what is organic chemistry? According to the American Chemical Society, organic chemistry is the study of the structure, properties, composition, reactions, and preparation of carbon-containing compounds. All life is based on building blocks and molecules that have carbon atoms, and interactions between those atoms and other atoms. To introduce a few introductory concepts, let's cover one of the simplest molecules that you can have in OChem. This molecule is known as methane, or CH4. Now if I were to draw out methane, it would look a little something like this. To understand why methane looks like this, we first need to look at the periodic table. Over here on the left side, we have a hydrogen, which is the smallest atom on the periodic table. It only has one valence electron and can make one bond. This is why you'll never want to put a hydrogen in the middle of a compound as the core of a molecule. Hopefully you've had practice making things called Lewis structures. If not, I'll be making a video pretty soon to explain how to draw those, but for now, I'm going to assume that this is a review for you, and you know how to do this. So we're going to take this carbon atom that is found in methane and put it in the center of our molecule. Carbon is in the second row of the periodic table, and is in the group that has 4 valence electrons. Putting the carbon in the center, we draw the valence electrons that are available to make bonds, which in this case is 4. After we draw out our valence electrons for carbon, we draw all of our hydrogen atoms that will each bring 1 additional electron. When all of this is said and done, we've made our Lewis structure where we show all of the electrons as dots. One thing to remember is that anytime you have 2 electrons between 2 atoms, we bring them together to form a bond, and we will not leave them as 2 dots between those 2 atoms. In other words, we're making a line. In this case, the bond we would be forming is a covalent polar bond, but there are different types of bonds, of course. If the difference in electronegativity between 2 atoms is huge, around 2 or greater, that's going to be an ionic bond. Ionic bonds aren't really connected all the time, and we're going to talk about them more in organic chemistry, but organic molecules are typically held together by sharing electron pairs equally between 2 atoms, which is, of course, covalent bonds. In this case, the lines between hydrogen and carbon and methane are all covalent bonds. As we continue on in this series, I'm going to give you a tip for drawing molecules. Basically, there's going to be a lot of carbons and hydrogens in organic molecules that we'll never actually really draw the carbons or hydrogens anymore, they'll just be implied, and you'll figure out what I mean when we start covering skeletal structures. However, for now, I want us to focus on some other things when we draw a molecule, such as the question of whether or not any of the atoms have formal charges. Well, you may be asking yourself, what is a formal charge? And if you remember back from Gen Chem, a formal charge is the charge on an atom within a molecule calculated by the formula. Formal charge is equal to valence electrons minus lone pair electrons minus the total number of bonds. In the case of methane, the carbon atom has 4 valence electrons and is paired with 4 hydrogens forming the 4 covalent bonds. This carbon atom has a full octet and is satisfied, so we would calculate the formal charge and find that it would be a neutral charge on the carbon and hydrogens, meaning that there's no net charge on the methane molecule. To show how this works, I'm going to draw out the atomic orbitals. Hydrogen only has the 1s orbital and thus is satisfied when having 2 electrons on its atom. Carbon has a 1s, a 2s, and a 2p orbital and will become satisfied when all of its shells are filled. However, this only applies to singular atoms. The reason behind this is that all of the valence electrons in the molecule need to be at the same energy level to be superstabilized in the case of methane. If we were to assume that the electrons bonding the carbon and hydrogen together went into both the 2s and 2p orbitals, the electrons would have different energy levels. So what happens, as in the case of the methane molecule, is that we form something called a hybridized orbital, or a hybrid orbital. We will be looking at the carbon atom here and will determine the hybridization of the carbon atom to be sp3 since there's 4 covalent bonds. What we will then do is draw out 4 electron pairs for the sp3 orbital since we have 4 sigma bonds. We'll then fill the orbitals out with all of the electrons coming from the carbon atom, and lastly, finish by adding all of the electrons from the hydrogen bonding. This last part you don't need to do, but this shows how all the carbon and hydrogen bonds in between in the methane molecule are equal in energy. If we take another look at a molecule known as ethene, which is going to be dictated by C2H4, you're going to notice that there's a double bond present between the 2 carbon atoms. Going back to general chemistry, we should remember that a single bond represents 1 sigma bond, a double bond represents 1 sigma bond and 1 pi bond, and a triple bond represents 1 sigma and 2 pi bonds. When more p orbitals are added, there will be stronger orbital overlap between the 2 atoms. This is why, in the case of bond strength, single bonds are going to be weaker than double bonds, which are going to be weaker than triple bonds due to the p orbital interactions. So we've gone over what OChem is, what Lewis structures are, bonding, formal charges, and hybridization, and now I want to get into some basic OChem and talk about constitutional isomers. Constitutional isomers have the same molecular formulas, but they have different connectivities, which means they have different properties and are completely different from each other. I know it's a lot to take in at once, so just hear me out. For example, let's take a look at ethanol, which is going to be C2H6O. Here we see that all the atoms, aside from the hydrogen, have an octet, which is extremely important in OChem. Here's the major rule for you to remember in this video, with the exception of one thing, which I'll cover later. Make sure that all of your atoms have 8 electrons. If they don't, you probably did something wrong when drawing your structure. Anyway, this right here is a proper structure for ethanol. There are no formal charges on any of the atoms since carbon has 4 valence electrons and oxygen has 6 valence electrons, and everything is balanced in the molecule. Now, what if I just rearrange the molecules to where it has the same number of each atom, so the same number of carbons, same number of hydrogens and oxygen, the same number of electrons, just with a different orientation? This structure right here on the right may look very similar to ethanol, but it's completely different. This is actually called dimethyl ether. The reason that the 2 molecules, ethanol and dimethyl ether, are so different is because of their properties. For example, ethanol can form a strong hydrogen bond with its OH hydroxyl group, and dimethyl ether cannot since there's no hydrogen attached to the oxygen. More hydrogen bonds lead to higher temperatures generally, and this is shown to be true here, where ethanol has a boiling point of 78 degrees Celsius, and dimethyl ether has a boiling point of negative 24 degrees Celsius. This could also be due to the polarities of the molecules. Oxygen tends to be more electronegative than carbon and pulls electrons towards itself, creating a dipole moment. In the case of ethanol, the dipole moment would be drawn towards the oxygen, creating a region of electron density near the oxygen, making ethanol polar. Once again, if we look at dimethyl ether will be nonpolar since the dipole moment will cancel out. As we continue the series, you will see how electronegative atoms can affect reactivity with other compounds, an essential part of OChem that you need to know. For now, let me give you a sneak peek into the next video where we will cover resonance structures and curved arrows. I'm going to draw CH2O, which is formaldehyde. If you look at formaldehyde, there's a dipole moment pointing towards the oxygen that is double bonded to the carbon, which has 2 hydrogens attached to it, and there's no formal charge overall. So what if we tried to draw a constitutional isomer like this? Well, this wouldn't work. While everything may look alright at first glance, it turns out that the carbon doesn't have a full octet and it would have a positive charge on it, whereas we want our molecule to have no charge overall. And what about this structure? You may also think that this structure won't work, and you'd somewhat be right. This is not a constitutional isomer since all the atoms are in the same positions as formaldehyde. However, this is what is known as a resonance structure, which in basic terms is a structure showing the movement of electrons in a structure. The reason this structure is allowed is because of the formal charges. Here, carbon is positive since it is missing a bond, and you might be saying, oh, but wait a minute, you can't do that to carbon since it doesn't have a full octet. And to that, I'll say, yeah, generally. However, when drawing resonance structures, we just ignore that rule. And you might be saying that this is still wrong since there's a positive charge, and while that's also true, we need to take a look at the oxygen atom next to carbon. we see that it has a formal charge of -1, making a negative charge that cancels out the positive charge on the carbon. This makes the entire structure neutral. We will cover this more in the next video if this seems confusing right now, but for now, try to understand the concept shown in this video before moving on. I've attached a free practice set down below so anyone can look at it and use it, and all I ask for in return is that you subscribe, like, and share this video with others so I can grow this channel and help others. Thank you, and I'll see y'all next time.